Good evening, guys. Hope you're doing well. I'm going to go ahead and share my screen and we can start our discussion of reaction rates. Hopefully this will be a good and clean discussion for us. So let's see what we can do. So when we talk about reaction rates, we're talking about how fast does a particular reaction proceed. Not only how fast does it go forward, but also how fast does it reach equilibrium. We want to know how fast these things happen. One of the reasons that we might want to know something like this is to know how long it's going to take to have a half-life, that kind of thing. We can use that for radiocarbon dating. We also might need to know how long is it going to take to make a particular amount of product. There are a lot of reasons that we might want to know how fast a particular reaction is. So that's how we're going to take a look at this and see what we can do. So hopefully there are no questions, comments, problems. If anybody has any, please let me know. I think you know that email, phone, office hours, all of those work. And hopefully we can take care of any questions that you have. So we're going to be talking about reaction rates. This is from chapter 13. This specifically talks about sections 1, 2, and 3, which is reaction rates, concentration and rate laws, and concentration and time. So there are a couple of things that we'll need to deal with when we do that. All right. So kinetics, when we talk about kinetics, it's the study of the rate of reactions. So it also provides information on the mechanism of a reaction, which shows the path by which a reaction occurs. So one of the things that you'll see is as we start talking about kinetics and looking at what a rate law is, how we determine a rate law, excuse me, sorry, sometimes what appears in that rate law does not appear in the overall reaction. So that leads us to talk about what the mechanism is and how this particular reaction occurs. All right. So reaction rates. The rate is the change in concentration over a change in time period. So change in concentration over change in time. So delta means change in, concentration means molar concentration, so the little brackets, molar concentration, T represents time. We can measure an average rate, an instantaneous rate, or an initial rate. Okay, all of those are used in different contexts, and it depends on what kind of data you have, what you're going to be looking at, right? So we follow the reaction rate by looking at the change in concentration. We can do this as a change in how fast the reactant goes away. We can look at how fast a product appears, that kind of stuff. So we can measure the change of C4H9Cl, and the average rate is calculated by the change in concentration over change in time. And the table shows the average rate for a variety of time intervals. Okay, what you should know, what I hope you know, is that as time goes on, that rate goes down. So as we have less material, we're going to go slower. So the more material I have, the faster I should go. That also implies that as we get things moving, we don't have as much going away. Sorry, I'm so sorry. We don't have as much going away because we've reached equilibrium. And so even though things are still going to be reacting, we aren't noticing it as much, okay? So we can plot rate data. Plot of the data gives more information about rate. So we can look at the instantaneous rate at t equals 0. This is the initial rate, okay? And it's taken by looking at the slope of this line at the initial time. We find that slope, that's our instantaneous rate. Instantaneous rate at time t equals 0 is the slope of the tangent to the line at that time, right? We can also look at an instantaneous rate at t equals 600 seconds, all right? That's our change in concentration over change in time, all right? So that's our instantaneous rate, okay? Rates are followed using a reactant or a product. Does this give the same rate for each reactant and product? Well, that depends. So one, we know that if we're looking at the rate of the reactant versus the rate of the product, their signs are going to be different. So as time goes on, the concentration of the reactant should go down. As time goes on, the concentration of the product should go up. So that's going to be opposite in sign. The other thing we have to think about is what's the reaction stoichiometry. So if our reaction doesn't happen to be a 1-to-1 ratio for everything that we're looking at, we have to make sure that we take that into account. So if I have 2O3 going to 3O2, and if I look at the concentration of O3, I need to divide that by the 2 of them. If I look at the concentration of O2, I need to divide that by the 3 of them. Okay. The average rate is proportional to the rate constant. So that average rate over the concentration change is equal to K. So a plot of the rate versus concentration will give you the rate constant. It's the slope of the line. For gases, you can use the following equation to look at the rate by measuring the change in pressure according to the following equation. So we can look at the change in pressure over time, and that's related to our concentration rate by 1, if we multiply that by 1 over R times T, T being temperature, as opposed to time here. So a couple of things that we need to know about reaction rates. We need to know the physical state of the reactants. So the more readily the reactants collide, the more rapidly they react. So if I'm in a gas phase, it's easier for me to react than if I'm in the liquid phase or the solid phase. And it's gas, liquid, solid, of course. Homogeneous reactions are often faster because they're in the same phase to start with. Heterogeneous reactions are that involve solids are faster if the surface area is increased. So if I have a fine powder rather than a pellet or a tablet, I have a very high surface area. That's going to go a lot faster than something that is not a high surface area. Sorry, I'm really sorry. I keep yawning. Reactant concentrations. If I have higher concentration, that increases my rate. The more of it there is, the faster it comes together. Since there are more molecules, the more collisions occur. If my temperature increases, then I react more because, again, more collisions happen at higher temperature. So reaction rate generally increases with increased temperature. Kinetic energy of molecules is related to the temperature, so they're going to move more quickly and run into each other with better collisions at higher temperature. Now, there's another thing that we can talk about, and that's the presence of a catalyst. So a catalyst is something that is not consumed during a reaction, but it can make the reaction go faster. Okay, it does not appear in the overall balanced equation because whatever we use, we get back. All right, they affect the kinds of collisions, changing the mechanism and bringing things together in a different way. Catalysts are often critical in biological reactions. They're very important for talking about things like that. Okay, questions about anything that helps us with reaction rates? Okay, these are things you should be able to speak to. So if I ask you what effect does the physical state of the reactants have, you should be able to speak to that. If I ask you what happens if I raise the concentration, what happens if I lower the concentration, what happens if I raise the temperature, if I lower the temperature, what happens if I have a catalyst, what does it do, what doesn't it do? Because a couple of times, often we'll ask you what the presence of the catalyst does and does not do. Okay. So questions, comments, problems about any of that? Hopefully not, but we'll see. When we talk about concentration and rate laws, so if we have a concentration and we can monitor it over time, that's great. We can, that'll tell us about the rate. But if I want to look at what's called a rate law, that tells me the rate at which these things change based on the concentration of each material. And it has what we call a rate constant, okay? So how do I determine what effect that concentration has? Because not all of them have the same effect in the presence of that reaction, okay? Every concentration, we keep everything constant except for one thing. And when we change that one thing, we see what happens to the rate of that reaction, okay? So look at this table of data in 14.2. That's rate data for the reaction of ammonia and nitrite ions in water at 25 degrees. Experiments 1 through 3 show how the NH4 plus concentration affects rate. So I have one set of initial conditions. I double the amount of the nitrite, oh Lord. I try, yes. I double the concentration of that. I see what happens to the rate. I then double the concentration of that and see what happens to the rate. Okay. In rows 4 through 6, I have a set of concentrations, and then I change the concentration of the NO2 minus and see what happens there. All right. So in that particular case, we're changing that one, and again, we're doubling and doubling to see what happens. Now, a rate law has the general form rate equal to the rate constant, K, small k, times the concentration of NH4 plus times the concentration of NO2 minus, each raised to a particular value. That value has nothing to do with the stoichiometry of that reaction. We cannot predict it based on an overall reaction. Now, we will talk later about how we can use a mechanism to predict that, but we cannot do it from an overall balanced reaction. It has to be determined experimentally. And that's what this data is used for, is to be able to do that kind of thing. All right. Now, I said for this reaction that it's NH4 plus to the 1, NO2 minus to the 1. How can I see that? Well, let's take a look. If I take the concentration of NH4 plus and I double it, and then I take the rate and look at that, it's also doubled. So I double the concentration, the rate doubles. That's directly proportional. So the order of that component is 1. If I compare lines 4 and 5, I double the concentration of NO2 minus and keep the NH4 plus the same. If I double the concentration, the rate doubles. That's directly proportional. So the order is 1. If the concentration doubles and the rate goes up by 4, then it's second order. Okay, we'll talk about that in a couple of minutes. If the concentration doubles and the rate doesn't change, then that's 0 order. It's not part of the rate law. Okay, so once we know the order of each component, we can add them together to get the overall order. Okay, so I know that I have a 1 for NH4 plus, I have a 1 for an NO2 minus, so overall it's a second order reaction, first order in each component. Okay, now when we talk about first order reactions, the rate depends on the reaction concentration raised to the first power. We can use the following equations to solve for A initially if we know what it is at a certain time. So I can find the initial concentration if I know what it is at a certain time. So my initial concentration is this A0. If I know what it is at a given time, and I know what that time is, and I know what the rate constant is, then I can find my initial concentration. I can also find what it's going to be at a specific time if I know the initial concentration and that rate constant. Okay, these are all forms of that equation that we can look at. Okay, now this is for concentration. We also have a version for pressures. So if we're all in the gas phase, then we can do this in terms of pressure. I'm not going to ask you about pressures, but it does work in a very similar way. And we saw the relationship between the concentration and the pressure expressions previously. Like I said, I'm not going to ask you about the pressures because I don't like dealing with it. So, and you can show me that you know what you mean with the concentrations without worrying about the pressures. And you can also use this equation to find the half-life. So the half-life is how long it takes for half of that material to go away. So for a half-life for first order, that's going to be 0.693 over K, where K is the rate constant. That rate constant can be found by plotting the natural log of the concentration versus time, and then that slope is the rate constant. Okay. Now, this is a bunch of information. I'm going to show you this for the first order, the 0 order, and the second order, and then we'll talk about what you need to be able to do with it. Okay, but I want to show you all of these things first. So again, this is first order. When we look at second order, the rate depends on the reaction concentration raised to the second power, or the concentration of 2 reactants, both raised to the first power. So again, we talked about that NH4 plus and the NO2 minus, both of those being first. If that whole reaction is second order, then it depends on both of them. Okay. Now we can use the following equations to solve for A initially if we know what it is at a certain time. Or if I know at a certain time what it is, then I can solve for what it is initially, as long as I have the rate constant. So this is just what we talked about before. But what you'll see is that this is a different relationship. Okay, previously what we plotted was the natural log of A versus time. This time we're looking at 1 over the concentration versus time. And then we get that slope just like we did before, but it's a different relationship. Okay, so based on which one of those gives me a straight line, I can tell which order it is. Okay, you'll notice that I can get a t1/2 also for this, and it's a different function than it was the last time. Okay, so again, we're going to go one more and then we'll do the comparison of these things. All right. Now we can do a pseudo first order reactions. So if I have a rate similar to the one that we talked about previously, the NH4 plus and the NO2 minus, if I make one of those rates or one of those concentrations huge, then it acts as a pseudo first order reaction. Okay, so if that one concentration is huge, it effectively becomes part of the constant, and we can look at what is the effect of the other material. Okay. Zero order reactions. The rate does not depend on the reaction concentration. So it doesn't matter what that concentration is. There is no dependence. Okay. So we can use the following equations to solve for A initially if we know what it is at a certain time. Okay. Rate equals K times A to 0. And A at a particular time is equal to negative K T plus the initial concentration. Okay. We also have a t1/2 for this. It's different than it's been in the past. We'll talk about that in a few minutes. And notice we can plot this data as just concentration versus time, and it's a straight plot. So there is no change in that rate as we change that concentration. Okay, the rate stays the same. All right, now that was a lot of data. Woohoo! Hopefully there are no questions about that, although I'm sure you have them at this point. What you need to take away from this? Well, we can use this to determine the orders. Okay, so we can use the types of ratio aboves to determine the orders. So we can look at how to, if I change this concentration, how does that affect the rate? And we do that by making it pseudo order in the other one. Okay, so we can do it that way. We can also do a plot of the data over time using the forms for each order. So concentration versus time for zero order. The natural log of the concentration versus time is first order. And 1 over the concentration versus time is second order. So if I do all three plots and see which one is the best straight line, that should tell me which order that particular component is. All right. Only one of those graphs should be linear. The one that is linear determines the order of the reactant. Once you know the order, you can determine a concentration at a specific time, the half-life, and the rate constant. Okay, so once I have that linear plot, I can find the rate constant using the slope. I also know which of the concentration expressions and the half-life expressions applies to that situation. So I should be able to work with those calculations, right? So all of these calculations are valid on the exams. But what you'll see if you look through the handouts is that while all of the the equations are provided to you, none of them are labeled with what order they represent. So that you need to know. So what you see here, you see the expression for the rate law, you see the concentration time equation. So if I know what the concentration is at a given time and I know what that time is, I can find the initial concentration. Or if I know the initial concentration and the time, I can find it at a given time and the half-life. So all of this information is going to be provided to you except this first column, the order. Okay, so that's not going to be given to you. Everything else is on the test. So once you know what order it is, by plotting it, by using some of that data to solve for it, then I can ask you questions about what's its concentration time equation, what's its, what is the concentration at a specific time, how long is it going to take for me to get a half-life, how much material is going to be left after this particular period of time, all of those things can be solved for. But you have to determine what the rate is to be able to do that. Okay, so rate first, then calculations. We will have practice with this in a little bit. I'm going to put together a practice for the third exam so that you guys can look at that. I'm going to do the practice for the third exam before I do the practice for each lecture so that you guys can see, what kinds of questions I'm thinking about for the exam, just to make sure. Okay, and then I will provide you with more questions if I can. All right, so questions, comments, problems on any of that. So hopefully the homework or the practice that you guys get, and I'm going to try and do that tomorrow, will help you to understand what it is we're going to be doing with this. Okay. I expect you to be able to do the following things. So I expect you to be able to look at a table like this and determine, much like we did here, what is the order for each of those components based on that table. I expect you to be able to plot data and see which is the best order. Now, let's take a look at what that actually looks like. So let's plot rate data for NO2. So we have a plot that we've done. We have concentration that we've plotted either concentration versus time. This is the natural log of concentration versus time. And this is 1 over the concentration versus time. Because again, we know that that's what is applicable for those situations. So you can see the zero order is just concentration. For the first order, it's the natural log of that concentration. And for the second order, it's 1 over that concentration. And I get the following plots. So this one is not linear, obviously. It has a line of best fit, but it's not a very good fit. Your R squared is 0.8627. For the first order, it's all right. My R squared is 0.9644, but that's not as good as my second order. So if I look at the second order plot, this has an R squared of 1, and that means that that is a linear relationship. So that is clearly a second order in that component. So that NO2 is to the second order, okay? And that's for this particular 2NO2 gas with heat. Gives me 2NO gas plus O2 gas, okay? All data is plotted, and since the second order R is 1, that's the best fit, and therefore the order of that reactant. NO2 squared. Slope is the rate constant. So K equals 46.452. Okay, that's what we read from this equation that goes with this. All right. Now that I know that this is second order, I can come back and look at all of this, and I can say, okay, that rate equals that constant that I just found times the concentration squared. I can say, okay, here's what the concentration at a particular time would be if I know that time and the initial concentration. And here's my half-life expression. So now that I know what the rate constant is, I can see how long it's going to take for me to get to a half-life based on the initial concentration. Okay? So there you go. That's the kind of thing I'm expecting you to be able to do. And like I said, you will get practice for that so that you can have some idea of how to do it. Questions, comments, problems on what we are going to do with understanding rates. So rates are measured in terms of changing concentration over time. We can do that for an instantaneous rate. We can do it for an initial rate. We can do it as an average rate. We can plot all of this data versus concentration, natural log of concentration, or 1 over the concentration to see what order that reaction is with respect to that component. We can do that independently for different components to see what their rates are or what the order is with respect to each of those components. Once I know what the order is, I can use these equations to be able to do calculations for that. All right. So those are the things that I expect you to be able to do. All right. So if there are any questions, comments, problems, please let me know. If there are not, then awesome. Thanks for being with me. I will talk to you very soon. Now I'm going to go ahead and stop sharing, and I will stop the recording, and I'll talk to you soon. Bye, guys.